Okay, we're moving on to the next homework assignment on the electronic structure unit. And I've noticed there's been a little printing problem with assignment 2 here. Anywhere you see a lambda, like right here, with that there, that's meant to be an L. For some reason that came out that way. Alright, so let's go over these. So which refers to a 2s orbital? Well, 2s tells us that n is 2 and s means L is 0. So I'm looking for one with n equals 2, L equals 0. If L is 0, m sub L can only be 0. M sub s can be either positive or negative 1/2, but C is our correct answer for assignment 2, number 1. Now looking at the second one here, we're looking for quantum numbers that are allowed, so we're looking for the one that is not allowed. So remember that n can be the positive integers, right? So 1, 2, 3, 4, etc. L can be 0 up to n minus 1. M sub L can be integers between negative L and positive L. And m sub s, of course, is either plus 1/2 or minus 1/2. So we're looking for something that violates that. Like, for example, if L is the value of n or greater, that would be a bad orbital. But what we see here is, in each case, n is 1, L is 0, that's okay. N is 3, L is 1, that's a 3p. It's okay. N is 2, L is 1, that would be a 2p. N is 4, L is 3, that would be a 4f. Those are all okay. So if we start looking at the m sub L values, we quickly see a problem. If L is 0 here, m sub L cannot be anything except 0. So that looks like that one is our wrong answer. If we look at all the other ones, the m sub L values are okay. 1, negative 1, that's okay. 1 and 0, that's allowed. 3, negative 1, that's okay. And then if we look at the m sub s values, basically they have to be either plus or minus 1/2. They're all okay. So A is the correct answer there, which is the one that's wrong. Alright, if we're looking at n equals 5 and L equals 2, m sub L is plus 1. The 5 tells us the energy level. L equals 2, L equals 0 is S, L equals 1 is P, L equals 3 is D. So this is a 5D orbital, so A would be the correct answer for that one. Which quantum number designates the shape of the orbital? Generally speaking, the shape is determined by the L value, B. So that would be what we go there. Okay, total capacity for electrons in n equals 3. So if n equals 3, L can be 0, 1, or 2. The s orbital can hold 2, the p orbital can hold 6, and the d orbital can hold 10. 2 plus 6 plus 10, that's 18. So C there. Total capacity for electrons in n equals 5, L equals 3. That would be a 5f orbital. F orbitals hold 14. And you can look at that again on the periodic table and see where the F region is there and count the 14 boxes. Alright, how many orbitals will have the following quantum number? N equals 4, L equals 1. So that's a 4p orbital, and that's going to be 3 orbitals which have m sub L values of negative 1, 0, and positive 1. It could hold 6 electrons, but we're asked how many orbitals. That's C. Now, when we're talking about how many orbitals have the following quantum numbers, n equals 6, L equals 2, so that's a 6d orbital, right? But then specifying m sub L as minus 2, that's just one of those 5 6d orbitals, minus 2, minus 1, 0, plus 1, plus 2. Those are our m sub L values of these 6d orbitals. So just that one orbital is specified by that, so that's B. Alright, we're looking for a 3p electron. 3 is going to be n equals 3. P is going to imply that L is equal to 1. So we're looking for N equals 3 and L equals 1, and we see that in B there. The other values are okay, minus 1 plus 1/2, those are all allowed, so that refers to a 3p orbital. Looking for a 4f orbital, again that's going to tell us N equals 4, and the F is going to tell us that L is equal to 2. And so I'm looking for N equals 4, L equals 2. That looks like B again for that one. All right, let's look at the assignment 3 now, and just knock both of these off in this video. So I put a couple of versions of the periodic table on the top of this assignment to remind you of the regions in the periodic table and how you can use the periodic table as your friend in terms of figuring out these electron configurations. And then you've got a normal version of the periodic table here as well to refer to. All right, so if we're looking for gallium plus, so if I go up here, gallium is right here, okay, 31. 31, if I translate that up here, that's right there. This is gallium. All right, so gallium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. That's gallium. If I do gallium plus 1, all I do is lose the 4p10. So that goes away. And so it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. And this is argon, basically. So we could write that as argon bracket 4s2, 3d10. And there we go. Answer A is that. You see they've written the order, the 3D in front of the 4s there. That's okay to do it that way as well. So A is our correct answer for that. Now when we're looking for manganese, element 25, that's right there. So that's, looking up here, that's in our 3D region. So we're going to go through again 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 1, 2, 3, 4, 5, 3d5 for manganese. So we're looking for something that ends in 3d5 that has the 4s2 and the 3d5 there, and that's B for that one. Electronic configuration of S2 minus, so we're going to take sulfur, we're going to add 2 electrons to that, so S2 minus is going to be isoelectronic with argon. We already said argon's structure is this one right here, 1s2, 2s2, 2p6, 3s2, 3p6. So I'm looking for that one here, and that's D for that one. So remember, whenever you're got a negative charge, you're adding electrons. If you have a positive charge, you're removing electrons. Oxygen 2 minus, oxygen is here. 2 minus, I'm going to jump over 2 more to neon. So it's isoelectronic with neon, and that's going to be 1s2, 2s2, 2p6. If we go down to phosphide, phosphorus 3 minus, I'll do that in blue. Right here, 1, 2, 3 minus. It's going to be isoelectronic with argon, so it's going to be the same one as argon. 1s2, 2s2, 2p6, 3s2, 3p6. Remember, what we're doing here is we're letting each box on the periodic table represent an electron, and to get the electron configuration, we start at number 1 and go up to the number of our element, or the number of electrons that are on our element. In a charged case, that's going to be more. So looking at bromine here, let's do another color. We'll get green this time. So bromine's right here. -1 means it picks up 1 more and becomes like krypton, which is element 36. That's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6 would be the bromide electron configuration. Now, looking at things like aluminum and arsenic, we're going to go the other way. So aluminum is +3. So if I start here with aluminum, if I lose one electron, I'm going back to magnesium. If I lose my second electron, I'm going to sodium. My third electron is going to take it back, and it's going to be isoelectronic with neon again. So that's going to be like oxide, 1s2, 2s2, 2p6. And then we'll use black for arsenic. Arsenic is arsenic, we're asked for arsenide, which is arsenic 3-. So we'll start with arsenic, which is here in the same column as phosphorus. Picking up 3 electrons, 1, 2, 3, it's going to be like krypton. So that's going to be like bromide, right? Yeah, like bromide is up there. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6 for that one. Now, if we're asked for the atoms that correspond to the following electron configuration, that tells us that there's no charge, right? They're the same atom, so oops on that question. So these are both the same. So if we look at 1s2, 2s2, 2p5, so I'll go up here to this one. 1s2 would be that one and that one. 2s2 would be that one and that one. 2p5, 1, 2, 3, 4, 5. That's fluorine, right? Translating it down there, so fluorine. And then to make the orbital diagram, we're going to use boxes or lines to represent the 1s orbital, the 2s orbital, and then we'll write our 3s orbital here, or 2p orbital, 2p orbital there. We've got 2 electrons in the 1s orbital, 2 electrons in the 2s orbital. Of course, they're paired. We put 5 electrons in the 2p orbital. First we put 3 in each orbital, and then pair up a couple of those to get 5. So that's the orbital diagram of fluorine. Remember, if we have the boxes written together like that, they're at the same energy. And remember, we could have written it this way. We could have said 1s, 2s, 2p like this. And again, up and down represent m sub s, and as -1/2 if it's down and +1/2 if it's up. And so that would also be okay if you did it that way. Now, on number 7, we're being asked about the symbol of the atom with this orbital diagram. This is 1s2, 2s2, 2p4. So that's going to be the element that's right next to fluorine. It's going to be oxygen in that case. And again, saying it's an atom means that the charge is 0. Now looking for neon. Neon has got that filled 1s2, 2s2, 2p6. This is neon right here. Asking for the correct orbital diagram for phosphorus. Well, phosphorus is going to be right below nitrogen, so phosphorus is right about there. So it's going to be ending in the 3p's, and we're going to have 3p3. So if we look at these possible orbital diagrams here, it's going to be one of the ones that ends in 3p. So it can't be A or B because it doesn't have any 3p electrons there. Then the question is it C or D? They both have 3. This one obeys Hund's rule to not pair those electrons up till it has to. So D is the correct answer. C would be an excited state of phosphorus. D is a ground state of phosphorus. Looking for calcium 2+. Okay, if we go up here and we look at calcium 2+, calcium's right here. We're going to lose 2 electrons, so they go back to potassium and then go back all the way around to argon, so it's going to be isoelectronic with argon. It's going to end in 3p6, as we've seen so many times. So we're looking for something that ends in 3p6. That's this guy. Everything else is good, so that is our answer to that. Now, the periodic trends that we talked about, the first thing is atomic radius. And we said that as you go down the periodic table and as you go from right to left on the periodic table, the atomic radius increases. It's increasing as you go down by the number of electrons or energy levels occupied. As you go from left to right, your effective atomic number decreases. So there's less attraction to the outermost electrons, so they aren't attracted as much. Ionization energy is the energy to take an element and take one electron from it, is the first ionization energy. This happens in the gas phase. The trend with that is related to the atomic radius. The further that outermost electron is, the easier it is to get rid of that electron, take away that electron. So if we draw it that way, we say that ionization energy decreases. And again, these are general trends, not necessarily. There's sometimes some bumps in those lines if we looked at those graphs on those, but that's a general trend. Then you have electron affinity. Electron affinity is the desire of the gas phase atom, we'll call it Y, to pick up an electron and become the negative ion. And what happens with that is that as you go across to fluorine and up, the electron affinity becomes more favorable. And it's consistent with the idea that things on the left-hand side of the periodic table tend to form cations and give up electrons. The things on the left-hand side tend to pick up electrons and become anions. All right, so hopefully that helps you with those homeworks and will help you be